So we're now live. Recording is on. So today we're going to be talking about unconstrained optimization. And the methods that we will discuss will mostly be, when we will move on to other methods, they will be based on this unconstrained optimization. There are methods for which we can directly somehow take the constraints into consideration, like for instance in the simplex method and in the methods of that we're using the linear that we introduced or discussed when talking about the linear optimization problem. But here we talk about general unconstrained optimization. So we're talking about real valued vectors or real valued function that takes as a parameter n length vector, and basically we're looking for that minimum of that. So I'll give over the years, let's say over the last 15 years or 10 years, the go-to example has changed. So now most of the people who encounter this minimization of some function will have encountered this problem with respect to machine learning. So you are basically minimizing prediction error or some classification error with respect to the parameters of a system. So the learning problem in most cases is reduced to an optimization problem. So for instance, if you're doing something like deep learning, which can be thought of, you can cast it as a just multi-stage nonlinear regression analysis, but you can also stage it as just optimization. So you're looking for a minimum of some error function and you're adjusting the parameters to minimize an error function. So we start with some function that maps Rn to R, and we're looking for its minimum. We have no constraints here, so we're just interested in what this function's values can be, and any point will do. So free problems are easier to deal with in this sense because we don't have to worry about the constraints, and many of the methods that we deal with later will cast the constraint optimization problem into an unconstrained problem by modifying the cost function accordingly so that its optimum would be found in the set that actually is our feasible set. Well, let's look at this. The main problem that we face, well, there are other problems, of course, that may be worse in certain situations, but mostly the main problem with unconstrained optimization and any optimization that deals with continuous variables is the fact that there is the problem of local minimums, meaning that it's a point such that if we move a little bit to any direction, then the function will increase. So it's a local minimum, but it may not be a global minimum, because if you move a longer way or if you move a little bit further from the point that you're dealing with, then you may end up in a point that is not local. So one way to just draw a picture here. I hope that you can see this now. So if we have here, this is my coordinate system, and I'm just taking one parameter function here, but let's say I'm looking for the minimum of this function, and then the function will have a behavior like this. Let's say like this. Then, can you see the picture I drew?
Negative. We cannot.
No? Okay. Let's see.
Maybe if you open Paint and you draw it right away.
I wonder why it's not showing. I mean, I drew it here. The annotation is somehow not sharing then. Let me, sorry. Okay, I'm still learning.
It's probably about whole screen sharing versus sharing a program.
Okay, yeah, let's do this. Actually, that's a good advice. So I'm going to do the whole screen sharing, right? So now I'm sharing my whole screen. And if I do the drawing now, can you see it now?
Yes, it's working.
Yeah, okay. So here's an example of a situation. I'm looking for the minimum of this function. And if I just look at, locally, let's say if I zoom in into a box and if I zoom in like in here, then I will find the minimum of the function in around that point over there. That would be my minimum there. So I didn't hit quite, whereas the global minimum is actually there. So my problem here is that if I look at just a derivative or some condition that tells me that, okay, it's going to increase in both directions from this point here. It's going to increase if I go left, it's going to increase if I go right. So this is what we know as, what is known as a local minimum, whereas the global minimum is found on that other point. Okay, so this is one problem that may or may not be easy to solve. It depends on the function. One reason why we discussed convexity is that the convex functions have the property that their local minimums are also global minimums. But if we are not dealing with convex functions, it is possible that there is no way to say whether the function has reached a global minimum or a local minimum. Okay, we will talk about this methods by which we can try to alleviate this problem in multidimensional situations. If we are dealing with an optimization problem like this, in very small number of cases, we can solve the minimum by simply, for instance, taking the gradient and setting it to 0 and solving the ensuing linear equation, not linear, but nonlinear equations for the gradient being equal to 0, and finding out that, okay, it has a unique critical point and so forth. So we can find a minimum point. But in general, this is hopeless. I mean, if you have a function that is in any way more complicated, then the minimum is nowhere to be found. And this is why we have to resort to numerical solutions and solutions that find the minimum by numerically finding one point after another until we reach a point that is a candidate for being the minimum. Here is a general template or general structure of these iterative methods that we are going to be using. So you can think of most, if not all, of the optimization methods that we will be dealing with that follow this kind of template. And the template works as follows. You start at some initial point. The choice of initial point is sometimes crucial, but we hope that it's not too crucial. So we choose a point from which to start. Obviously, many times the starting point can have a huge effect on where we end up or how fast we end up to where we are going to be ending. We'll talk about this a little bit, and we'll see examples of this. The second point of order. When we are at any point, so we start an iteration basically where we find one point after another. And if we are at the current point, let's call that xk, we somehow find a direction into which we move from here. So we need to say that we're at the point and we're in Rn, so the direction is n-dimensional. We're going into some direction. Let's go over there. And we hope, or we usually assume, we will develop methods by which we guarantee in certain situations that this is what is known as a descent direction. And by descent direction, we mean that we have reason to believe, or we know locally from some computation, we know that if we move into that direction, the function will at least decrease if we don't go too far into that direction. Obviously, if we go into some direction too far, then the function will start increasing at some point. But there is some t such that if we start at xk, then f at xk plus tk times dk, so t is a scalar, it's a real number, so t is the scale of the direction to which we go. So d is, let's say d vector is this direction, it points to that direction. For instance, let's say we've determined that it's safe to go at least some way in that, somewhat in that way. And t is now the scale. How far do we go? As t ranges from 0 to infinity, we go from here to infinity over there. And when t is small enough, we know that if we go that much that way, then we get to a point where the function has a smaller value than where it is currently. So if we have a differentiable function, for instance, then we can use the Frechet derivatives definition and the approximation, so that if we go tk times dk, which is the direction, then roughly the change is proportionate to the derivative at fk times dk. That here you have to think of this f prime at xk as a linear operator. So it's some linear operation on the direction dk times tk. And in this case, you can think of this as f prime as the gradient. So you can think of this as the gradient dot product with the direction times tk. So this is roughly the change in the function. So we see that as long as the dot product with the direction that we choose and the gradient is negative, then the search direction is going to be a descent direction. And to understand how this is, I'm going to stop sharing for a while. I'll just draw you a picture so that you can now see my video here. So I'm going to draw you a picture. So just to give you an idea. So in 2 dimensions. So very often the case is that I hope you know the concept of okay, let's say I have a function of 2 variables. So I'm moving, my space is this 2-dimensional grid here. I'm moving from one point to another, and my function gets different values. So let's say that I'm at this point here. That's my xk. That's the point where I am at now. And let me draw a line so that the f. So I'm drawing this line, and this line here is meant to indicate these are the points where the f gets the same value as this, right? So if my function is, if I'm not in a local minimum, obviously, if I'm in a local minimum, then it doesn't get the same value anywhere, but necessarily. But if I'm somewhere, let's say it's something like x squared plus y squared or something like this function, then if I move somewhere, then there are certain directions to which the function doesn't change. And let's say that it increases in that direction, right? So you can actually, I don't know how much analytical geometry and this kind of thing you've done. I'm not going to go into specifics or proving how it goes, but we can do this kind of thing where we notice that if this is if this curve here is where fx is equal to f at xk, if that dot here is xk, then actually we can get this line, and this is what's the word? It's a normal to this this line, or if it's a surface, then it's a normal to that surface. It's perpendicular at this point, if this is the gradient. And notice that if we go anywhere in here, somewhere over there, the function will decrease because it's going to increase in this direction. And this line delineates the points where it's equal. So as long as we go on this side of the line and somewhere in below this line, then the function will decrease, and over there it will increase, right? Okay, let's return to the all right. So we just closed. So now, choice of search direction. We want it to be such that the function decreases so that we get closer to a minimum, obviously. And we get these different algorithms based on what the descent direction is. So we will talk about the gradient method, the Newton's method, quasi-Newton method. Well, I'll mention the conjugate gradient method. We're not going to in-depth into the conjugate gradient method, but I'll mention it. And there are other methods also, but the Newton method and the quasi-Newton method and the modified Newton method, I'll mention those. Those are the ones that we will discuss most. The gradient method is relatively simplistic. If you've dabbled with machine learning, then the so-called backpropagation algorithm for neural networks is basically a gradient descent method by which, you know, your function is an error function of the classification errors that the network is making, or the prediction errors if you're using it in that way. And then the gradient descent method is, you know, changing the parameters of the network in such a way that you're doing basically what is called the gradient method to minimize the error, classification error or prediction error of the network. So if you are into machine learning, then that's what's happening there. And actually, it's pretty much what is going on. And you know, you can cast many of those methods by which we teach neural networks as optimization problems, and actually even most of the solutions are here. There are these methods that combine gradient methods and Newton methods and so forth, like Levenberg, Margard, and those. I'll see if we can mention some of those during this, but it's a whole field of it's more of an art than science, in the sense that there are all these parameterized methods by which we choose these descent directions in a clever way, and there's no all-encompassing theory here. So I'm actually going to just present here this general template of these functions, of these methods, and we'll discuss some of the most common methods. But you be aware that they can be tinkered with, they can be adjusted. There are all kinds of situations where you can make small changes in them. Third order of business is to find out, okay, second order of business was to find the direction to which we go. Second order is to find how far do we go there. Again, how far we go there, that is a matter of tinkering and trying out, and trials and tribulations, if you will. You know, you want to find a certain step length there. For instance, in machine learning situations, this is called you have the learning rate. Usually that's actually your step length there. So you go and change your parameters by a certain amount before you calculate the error again, and see how it worked. And the step length is basically that. So the choice of the learning rate is actually the choice of the step length there. So it's following this template to the T, so to speak. Then you iterate, you find the new place where you go, the new point, xk plus 1, it's the old point plus then the step length times the direction. And that's it. Almost. Obviously, I mean, you won't do this infinitely long. You repeat these steps until you satisfy what is called the stopping criterion. So the stopping criterion can be one of many, many things. Again, the stopping criterion determines basically what kind of algorithm, I mean, one of the parameters or one of the choices you have to make in devising the algorithm. There are things like, you know, if the gradient of the function is close to zero, then stop. If you've reached a certain number of iterations, then stop. If you used a certain amount of time, then stop. If the point from which you started and the point you ended, I mean, the difference between the last two iterations was small enough, then stop, and so on. There are various ways by which you can decide when to stop running the algorithm. More often than not, in real life situations, when you stop is actually a matter of you know, it's a social situation. You know, you have to decide it for reasons that have no mathematical, not mathematical, but for social reasons. Like, for instance, I'm running this optimization problem to find the best parameters for my system. And it's already pretty good, but it's getting better by every iteration. But every time it's getting a little bit less better. And then my boss says, look, I need some solution right now. And I said, well, let's go with the one we have. So that there's a social reason, not a mathematical reason to stop. So sometimes it's a matter of finding a point that is good enough, right? Mathematically speaking and strictly speaking, this algorithm only makes sense if we can prove that this iteration somehow converges to an acceptable solution of the problem. In practice, such proofs are a pie in the sky. I mean, difficult, a lot of work, even impossible, you know, not necessary even. I mean, if you can demonstrate that you get better points, you get better solutions by these methods, then use the better method, you know, use the better points. So more often than not, in real life situations where you need to do optimizations, you have a solution somewhere, you have a point, and you know that it's not optimal. Use an optimization algorithm to find a better point. And you know that that better point gives you a few percent of decrease in cost or savings of some order of magnitude, or, you know, some small, when I say order of magnitude, some small order like 10% or 1% or even 0.5%. I mean, if we're talking about large costs, then even a 1% saving is a lot. So you are content with any improvement you get very often in the real world. Obviously, when you're dealing with mathematics, you would like to have a proof of convergence, proof that if I just keep on at it, I'll get an optimum point. And that's most of the time we'll discuss how this is done and what kind of conditions are sufficient for that, but we will mostly skip these proofs and give some guidelines instead. So from this point onwards, much of what we will do will be more of an art than science in some sense. Well, science maybe, yeah, in the sense that we can do empirical tests on it. Yes, so it's scientific work, but it's more like experimental science than mathematics, in the sense that we cannot necessarily prove convergence. We can just demonstrate that we get better and better points. There is a sub-problem in here. So you can think of this as an optimization problem from R n to R, but there is a sub-problem here, which is stage 3, finding the step length. So the step 3, you can think of this as a line search problem. So you've reduced the problem of finding a solution in multiple dimensions by fixing the direction into which you go, and then it's just one-dimensional problem. How far do I need to go there? So many of the situations where we discuss these different methods, like Newton method, quasi-Newton method, and so forth, we will be discussing also, as part of the big problem, the line search problem. So once we've decided which way we go, then we have to decide how far we go there. And here are a few things that we need to do. So one of the things is where we can cast this problem of finding the step length into minimizing GT, where G is kind of a function that is constructed on the spot by taking the function f at xk, where xk is fixed, dk, where dk is fixed, and then it's just xk plus dk, which is the it becomes a one parameter problem, and we just solve this to find the step length t. And there are several ways or criteria that we can do. One, A, the minimum is attained at 0 of the derivative. So if it's a decreased direction, it decreases. So this is the derivative with respect to t of this g. So g prime of t is going to be negative, and we can go into that direction as long as it remains negative. Once it's 0, we've reached the point where it no longer decreases. If we go further, it may start increasing. Of course, obviously, we can have let me just draw a picture again. So obviously we can have a situation, let's say we reduce this into line search. You can see now what I'm drawing, right?
Yes, we can see.
Yeah, good. Then let's say we fixed here, this is my G here. And I start at some value here, and I notice that it's going down, 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 and it starts doing like this. It is possible that it will go like this, and then like this. So I'm just saying there are certain criteria. First, we can find this. This was supposed to be the 0 of the derivative. So there's a flat point there. I mean, a saddle point. My drawing may not contain an actual saddle point because of my wobbly hand, but you see what I'm saying. Here we would have the 0 of the derivative, but it's not actually even a minimum. I mean, we can still go further. Here we have another minimum. We can go this far. Maybe it does another one like this and then starts increasing. And, we have these different situations. So the third point would be a global minimum. The first point would be a first critical point. So it's the first point where G prime is 0. The second point would be the first local minimum, where it's an actual minimum, and so forth. So we may have any criteria. In fact, we will have a point of choosing actually basically any point. We could have a decrease as long as we're choosing any point. Oh, sorry. My hand is not steady enough for this. So as long as we basically pick any point in between here, then it will decrease. The function will decrease and we get a better point. Obviously, there is no obvious way of saying which of these points is best, but different strategies will give us. Well, I would say that there is a strong argument against picking a local maximum like the red line here. So there is probably an argument be made against picking that red point there. But other than that, we may end up settling for actually any point in between there. In general, we don't have this kind of a line here drawn analytically. In general, we don't have this. All right. So I hope this gives you an idea of what is going on. Right. Like we said, there are no proofs, or in general, there are no guarantees in general that any of these methods is better than the others. There are convergence proofs or something that usually assume that either it's a local minimum or it's a global minimum for the algorithm to converge. We'll not discuss this so much, but you have to pay attention to the fact that it does sometimes matter from the theoretical point of view, but which strategy to choose there are situations where you have no other way or no recourse but to just empirically try different approaches and see which results in the best convergence. There are warnings here, like, you know, if we have proven some results and the step length, if the proof assumes that the step length is an exact minimum, and numerical approximations give us a point that is close to that, or at worst, I mean, even worse, it may give a point that is not even very close, but it just resembles numerically, you know, locally, it resembles the minimality criterion without actually mathematically satisfying the conditions. Like, for instance, if we are looking, I mean, when in my drawing, if we assume that it's 0 of the gradient, and let's say there is a almost flat point there, which is a saddle point, and we choose that, and the theory assumes that it's an actual minimum where it's going to start increasing for convergence, then it is possible that our algorithm or our method fails to provide us with the optimum point if we choose this line length. So there is no substitute for trying to understand and trying to figure out how the actual problem behaves locally and globally. So you know, you should try these out empirically, but then you should also do double checks. Like, for instance, if you reach a point, you know, try some points around it. Do I get better, or is it, you know, there are situations. We'll see examples of this. If the convergence of the algorithm doesn't require any of these strategies, it's just that, you know, step length, if we have a long step length, if we go too far, then the algorithm may oscillate. So we get, if the step length is too high, we go too far, so we go past an actual minimum, then we go back again and past, you know, we are flip-flopping around the actual minimum. On the other hand, if the step length is too small, you know, the algorithm may decide that it's, you know, it may become smaller and smaller, and we may have a stopping criterion, for instance, that when the point doesn't change too much, then anymore, then we are content that it's a minimum. This actually happens in a lot of like neural networks and machine learning situations, like if you're using the sigmoid function. So I'm not sure if you're familiar with the sigmoid functions, but one way to explain it is like 1 over 1 plus e to the minus x, and that is it results in a situation where the function has, when you're far away from the origin. If you're far away from the origin with respect to one of the parameters, then the function is very flat, and numerically the partial derivative may look like 0. And if you are at a point like this, it may look like you're close to convergence when you should really be actually moving towards 0. But for one reason or another, you've ended far from the origin, and your actual optimum is close to 0. Then you run into this problem that you know, you're ending prematurely when you should actually be driving in some direction, but the direction doesn't look promising enough because the function is very flat, and it only when you go far enough does it start to actually decrease. So this is something to be aware of, that, you know, shorter step length, yes, more robust and less prone to oscillation. Longer step lengths, faster convergence, but oscillator behavior. And that's why there are adaptive ways to do this. Like, you start with longer step length and then you shorten it once you are content that you know, you're not getting stuck and so forth. So there are these different ways to do. I'm not going to go through how this goes in great detail. One order of business is like, there is some value that you know, you want to choose a step length such that there is some criterion of how much smaller should your function go. You know how much of a difference should it make. So you make sure that the step length is not too small, so that your step length is not too large, so that you don't aim for the pie in the sky, you don't make a too big difference, And also, your step length is large enough so that you're not making a too minuscule a step. So there are different ways of that, of doing that. And also then there are ways of like, for instance, if you end up taking a large step according to some criterion, then you make the step shorter. So repeat it until the step length becomes suitable so that the oscillation can be avoided. But we're not going to be talking about this step length too much. I just wanted to mention that this is a sub problem, and especially those of you who work with machine learning or are going to work with machine learning will have to address this step length issue. So the learning rate issue is a very crucial one in machine learning environments where you're usually running an optimization algorithm very much like this. Yeah. So we'll talk about stopping criterion shortly, but I'm going to now stop the recording. All right, we are back live. So the next thing we need to discuss is, this discussion about, or this considerations about step length, we're not going to go very deep into that. We'll figure it out in every situation separately, and we'll talk about that shortly when we get to the methods. We'll get to the actual methods next week. Yeah, so that's not going to be long now, or maybe even maybe even Thursday. Also, the stopping criterion, there are ways in which we can decide when to stop. Here are 3 examples, like stop the iteration when the proportionate change in your point, if your point does not change proportionately very much, then you stop, meaning that the norm of change is smaller than some factor of the norm of the actual point. Like, let's say if there's a 1/1,000,000th, less than 1/1,000,000th in the change in the norm of your current point, then your point is not moving very far proportionately, and you can stop. The tolerance, we can discuss this tolerance. It can be either a fixed number or a function of some sort. We'll talk about it shortly. The other situation where we can, another way in which we can look into this is to look at the proportionate change or the absolute change in the value of the function. So if the value of the function does not change by much, so this is like tolerance, it can be either a fixed number or it can be some function of x or some function of f of x. In any case, if the change in the function's value when you move from one point to another, if the function doesn't change by much, then you stop. Again, both of these approaches have their own pitfalls. They have their own pitfalls in them, and some of the reasons to this may be, so first let me mention one pitfall. If you have very sharp change in the gradient of the function and you're going to a local minimum, then you're making a very small step, and it's a very steep local minimum or something like this, in that direction. Obviously, you have various directions, and in different direction it may decrease or increase, but let's say in this decrease direction you have a very sharp drop in the function, and then it's immediately very quickly starts increasing. Then you stop the iteration by this criterion 1 because you didn't move very far from point X. But this may be a problem that relates to the behavior of the function. So if the function has very big changes in the derivative, for instance, so that a very small changes in x results in a big change in the derivative, then the criterion 1 may be sensitive to this kind of thing where you stop prematurely. The second criterion, if you have flat surfaces of the function where you should go pretty far, but the function doesn't change very much when you go. So if your learning rate, I would say learning rate, but if your step length is small, too small, then you may stop prematurely if you use this criterion too, because you're taking the step length, a short step length, the function doesn't change much. You should actually take a longer step and the function would change. You'd get a much better change in the function, but you're deciding to stop early. So there's a risk there. Number 3, criterion, look at the gradient of the function. If the gradient has a norm that is very small, so it's pretty much close to 0, so you appreciate the fact that it's not going to change by much. So this has pitfalls in it too that depend on the function. We'll see the so-called banana valley function, which has a problem relating to this CR3. All of these are just examples. There may be other criteria. Like I said, there is a social criterion. You run it for as many iterations as you can until your boss says, I need the numbers. Okay, that's one possible situation. Here are certain situations with which or certain criterion or certain perspectives into what we can say about convergence. So convergence means that when you're moving from one point to another, then absolutely convergence, whether or not there is convergence if the sequence of points, when the number of points goes to infinity, does in fact converge. The limit of the sequence of points is the optimum, or at least a local minimum. I mean, we're not sure about whether there's a global or local minimum we're going for. Well, let's say that we're looking for a local minimum, a global minimum, and there is, let's say that the function is pretty much convex. So let's say it's not entirely convex, but it's pretty much convex, or the convexity of the function is to the extent that there is that we're not bothered by the local minimum problem. Then even so, up to infinity, the function, the method might find us the minimum of the function. Then it may not be enough. We may be worried. We need to be worried about how fast do we get there. So looking at from the point of view of criterion 1, so, relative change in the actual point, and we are kind of thinking of x star as our limit. That's the point to which we are converging to, and we're looking at, well, how fast are we going to get there? And we say that convergence is linear if it's linear in the proportion. There's a constant c greater than 0 such that the next point is always closer than c times the previous point. So the distance to the actual point drops proportionately. Meaning, for instance, if c is 1/2, then it means that we are converging towards the point by always moving 1/2 of the way there. So that's actually pretty rapid convergence. We are getting, if you think about it in terms of bits, then we are getting one more bit of accuracy in representation of the actual point. So that's actually pretty rapid convergence. Superlinear, we say this Q superlinear. If the proportion, if you think of this, if you look at this linear constraint, if you have, it's called Q superlinear if this proportion goes towards 0. So meaning that the rate of convergence is so fast that the next point is always more closer proportionately to the previous one than the previous iteration was. it's a bit hard to explain this, but the proportion of the distance goes to 0. So you're actually going very, very fast to 0. Superlinear, not Q superlinear, but superlinear, if there is some alpha such that you have something like linear convergence, but in fact, the closer you get, the faster it converges in terms of there's an alpha, which is a power of the previous one. So let's say some number between 1 and 2. So if you have 0.5 to the power of 1.5 or something like this, it gets faster than linear. It gets to 0 faster than linear. So the smaller the distance, the faster the convergence. And quadratic, if it's quadratic, meaning that there is a constant c, and then if you're close enough, then it's the distance to the power of 2. Remember that if the distance gets smaller than 1, then raising it to the power of 2 makes it quite a bit smaller, and it also has this coefficient c, which is some coefficient. Usually that's considered to be smaller than 1. Obviously, if it's bigger than 1, then it's not very impressive in the linear case, at least. But probably it should say in the linear, it should say c is between 0 and 1, because if c is greater than 1, then obviously the linear constraint doesn't even guarantee convergence, right? Also, for convergence, we say that convergence is global if the convergence happens regardless of an initial point. So this is just a vocabulary for talking about convergence. We're not going to talk about convergence too much. We're going to mention these results, and we're not going to prove them, because the proofs are always tricky. They're often very involved and beyond the scope of what we can teach here. But I'm going to mention some of these convergence results. This classification is something that you don't need to understand or learn, but it's something that it's here for reference. And if you are going to delve deeper into optimization, then you should know these concepts and see that the rate of convergence and whether or not convergence is global are issues that should be dealt with when you're developing methods for optimization. At least if you're developing the theory of optimization. In practice, not so much. You may tinker around and empirically try to figure out how quickly you get to optimums. All right. Let's talk about these methods. I mean, for the line search, we need to have one-dimensional minimization. So remember, to solve the line search problem, to solve the line length problem, we are minimizing GT, where GT is like you're casting the problem of finding the minimum of f into one-dimensional problem by first choosing, okay, I'm going to go that direction, and then we minimize the function with respect to that direction. And here are certain things that we can do for that. And I'll mention some that may be familiar to you from prior situations. So remember that we can then cast this g prime of t as just taking the gradient of f at xk plus t dk. So it's times the dot product with dk. You can calculate the derivative of this f. Derivative with respect to t, and you get it that it's the gradient dot product dk. That's your derivative at t. And the second derivative can be obtained by taking the Hessian matrix of f. So that the Hessian matrix is the matrix of second order partial derivatives crosswise. So the element ij of the Hessian is the partial derivative of f with respect to xi and then with respect to xj, and it's symmetric because derivative is linear, so you can take the partial derivatives in either order. So it's a symmetric matrix, this Hessian, containing the partial derivatives of f. And you calculate it at point xk plus t dk. And then that's your second derivative. So here is called what is called the Newton method for finding the actual step length. Remember that we're now solving this one-dimensional problem with the Newton method. There is this we will talk about the Newton method when it comes to the whole n-dimensional case, but this is the specific problem that has been cast into the one-dimensional case where we're only solving for the step length. So we can do this, like we enter into this what might call a mini game of optimizing with respect to t. And so we fix in our algorithms, we fix the search direction there. Then we go into an iterative search on how far do we go that way. Okay, we found that point. Then we find a new d and we go that way. And this is now the mini game of finding how far do we go to the direction of d. So if we solve this, we use this approximation. Remember, this is one-dimensional problem, so we can use Taylor formula that should be familiar to you. We can approximate the first derivative, g prime at t, which is just a number because it's one parameter function. And its approximation is, we start at any tk and we move towards t. And we can get this by taking, again, the second derivative. So we are at g prime tk plus g prime prime tk times t minus tk. So if you think about this, it's just Taylor approximation. I hope you know the Taylor polynomial. So you can think of g prime as a function on its own. It's the derivative of g, but don't mind that. We take the derivative of g prime and we use that to approximate g prime. And the same approximation, this Taylor form, which we say by Taylor formula, we can also take this from the definition of the Frechet derivative. But this is something that you should already know from previous courses. Now we solve this equation by setting this g prime at t to 0. But instead of setting g prime at t to 0, we set the approximation to 0. This is known as the one parameter Newton formula. And it's there to find the minimum of a function. So basically the 0 of the gradient or 0 of the derivative. And we solve this to get to what is t. We solve this equation for t and we set that to tk. So let me just, I hope you can see that what is going on there. So I'll do this math for you. I'll stop this share so you'll see my screen better. So in it says that our g prime at t is approximately g prime at tk plus g prime prime at tk times t minus tk, right? So this is what it says. This is the approximation. We're approximating g prime at t. And we're currently found the page at tk. Originally, tk may be like, let's say it's 0. T0 is equal to 0, for instance. I'm solving this for t. When I write that equal to 0. So I set this to 0. So I look at where it's approximately 0. So I solve this, and I get here that t minus tk is equal to, so setting it to 0, I just solve that t minus tk is equal to g prime at tk over g prime prime at tk. So I solve it for that. Just a very simple thing. I put everything on the left-hand side and then I divide by g prime. All right, let's return to this. So from this, the next stage is that tk, I solved this for t and set that to my tk plus 1. So It should be mine. I should have had the minus there. Sorry. Yeah, so in I forgot to put the minus there. There was supposed to be a minus. Now, I've solved this tk plus 1, and now I can set this. I noticed that there is the gradient of t, and then there's the Hessian of that f on the. So this is just casting this back into the in terms of using f, and it has the second derivative h. So if you ask the second derivative of the Hessian, then we're doing it. We continue this iteration until we get close to g prime at t being close enough to 0, and we've now solved the step length. So this is then our xk plus tk dk, and we stop at there, and then we go to the higher level algorithm, and we continue from that point onwards. It is known that if we are close enough to the 0 of the derivative, then there's a quadratic convergence. This is pretty rapid convergence. We get very fast correct digits or correct bits of the, if we're doing this numerically, then we get very close to the actual minimum very quickly. So this is very fast. There is only one problem here, is the high dimensionality of this Hessian matrix. So especially in machine learning environments, I mean, the number of parameters, meaning because we're minimizing with respect to parameters, that means the X has dimensions that are ridiculously high, sometimes thousands, even tens of thousands of variables. So whereas, let's say 1,000 variables, it's fairly quick to calculate the gradient. I mean, 1,000 computations is not that much, but calculating the Hessian, it's 1,000,000, so it's a lot bigger. And if you have a 10,000 variables, then calculating the Hessian amounts to 100 million computations, 100 million partial derivatives. So it's not feasible to always calculate the Hessian. So we call this the second method, or the secant method. I'm not actually sure how that is pronounced. So in that, we don't use the Hessian. Instead, we approximate the Hessian, which is kind of like the approximation of the Hessian is supposed to be the second derivative. So it amounts to the change in the first derivative, right? And instead of using the actual change in that is approximated by the second derivative, let's just use how much did the gradient itself change. So that's far easier and less computational heavy. So we can approximate it with what is called, we call this the secant method. I mean, it's the secant method comes from the second method. I don't know how to pronounce that, but it comes from this idea that if we think of this as a derivative here, or like this, I mean, then instead of finding the derivative of the derivative, which in this case would be the second derivative, which gives us basically the tangent at that point. Instead, we can take the secant, which is basically the change between 2 points, right? So it is not actually the tangent, but between these 2 points, there is a point at which this is a tangent, but it's a little bit off. If we take it there, then we're going there. So it gives us a little bit of a off approximation of the derivative, but sometimes it's good enough. So this is called the second method, or secant method. Again, I'm not sure how to pronounce that. So in that, we approximate the change, the second derivative with the change in the gradient. And in terms of f, we get this converges q-super linearly. It's pretty good, and we can use this method by which we can find the 0 of the gradient of the g, which is now, remember, we're still just only doing this one-dimensional case. Now, you already know this by now, that we are basically, what we are going to be doing is we're going to be relying on the differentiability of the function. and also the second derivative. So most of the case, if the number of parameters or the number of variables is small, and or the function is sufficiently well behaved in terms of what its second derivative is, then we can use the Hessian there. But if it's not, then we will have to resort to some other means by which we approximate how does the gradient, how is it going to change. That it may involve, for instance, in the second method here, it involves just actually looking at the difference of the gradient. I mean, how did the gradient actually change? Obviously, for non-well-behaved functions where the gradient, wiggles around a lot or something like this, or does abrupt the second derivative, or even, you may have to consider even the third derivative. So if the third derivative is very, very big at some point, so that the second derivative changes rapidly, then this may give a bad approximation, but under sufficient regularity of the function, then it should be doable with the second method. It should not be too bad. There is also a problem in situations where we're not differentiable, or the derivative is too hard to compute, or it's somehow nasty in other ways. So we can use, if we have a function that is what it calls unimodal, so we know that in some interval there is an actual minimum, and before the minimum the function decreases, and after the minimum the function increases. But let's say that the decrease, maybe it's piecewise somehow, like it does abrupt changes, so that derivatives are really bad there. So maybe it's like a, let's say the function looks something like, I'm going to draw a picture here. Let's draw something. So let's say that the function, here's my, and just try to emulate it. So between, here's A and here's B. And we say that it's unimodal. It means that there is a minimum somewhere in between there, A and B. And but it's I'm trying to, okay. Let me just do it like this. So let's say that it's behaves something like this. And there are a lot of points at which it's not differentiable. But it does inch downwards. And then upwards. It's not supposed to have a local minimum, but it's supposed to have these corners in it. So let's say it's not regular enough so that it's got, the idea here is that it's not differentiable. There are many points at which it's not differentiable, so we can't really use the derivative, but it does have this behavior that there is a minimum somewhere, right? You get what I mean? You're seeing I hope you're seeing it. So here, that's the point of the minimum. So if we know that the function behaves a little bit like this, then one way to do this is to make use of this unimodality by doing iteratively as follows. So we divide it into 3 sub-intervals. So let's take, for instance, there and there. So we have 3 sub-intervals. And we look at these values of the function at the edges of these intervals. And let's say the value at B. So, and in this case, this C and D, let's call this, I'm going to draw here. So this is my C and this is my D. So basically what this means is that we are going to try and figure out which of these intervals, AC, CD, or DB, contains the minimum. Because it's unimodal, we can deduce that in this case that because C is below A and D is below B, then we can deduce that in fact the minimum can be found at between C and D. But then, you know, it may be the case where we yeah. Well, basically we can then divide it in different ways, and notice that there are situations where we can rule out. In this situation, we can rule out. I'm going to just do this. In this situation, we can rule out this DB, right? Because we know that it decreases from A to C and increases from C to D. Then the minimum must be somewhere between either between C and D or A and C. All right. Alternatively, I mean, if the value at D would be smaller than the value at C, then we could rule out AC, right? I mean, now we can't rule AC, but we can rule DB. But you know, you see, we do it until such a time as we find a small enough interval and we are content that we are close enough to the minimum. So this is one way to solve the one variable case if you don't have use of derivatives. Even if you have use of derivatives, but you can't really trust the derivatives because they wiggle around too much or they're not good enough. You can have a linear convergence. You can have a linear convergence here with C equal to 2/3, right? Because you know you can always rule out 1/3 of the points that were available. So you have 2/3 of the way to the optimum. I mean, in some sense, if you take the middle of the region, then you're all the time you're getting closer and closer. If you use this method, there are other ways of interpolating. You can find an interpolating polynomial and find out methods by which you can find out a better approximation, rule out more points, and so forth. So these come in handy when your function is not necessarily reliably differentiable. So you know, you can't be sure that you find a very good point in between other than using this method. So that's one way in which you can address this issue. Okay. I'm not going to go into the gradient method now, not yet. The gradient method is a higher level method. So anything up to 4.1, this discusses 4.1 discusses the line search problem and how we solve the line search problem. We will, in general, in this course, be using numerical minimization functions provided by MATLAB, but we can discuss this a little bit more if you find that this is something that you want to discuss. Also, if you're working in things like machine learning or something like this, where the line search problem is an important sub-problem that you need to focus on and you want to talk about it or research it or learn about it a little bit more, then the modeling exercise and the exercise that, you know, your modeling exercise task, one way of utilizing or capitalizing it would be then maybe you want to do that about do it about the line search problem in your own field. If you're working on something where you need to figure out what how the line search problem is, if it's crucial to something that you are interested in, then that's one possible place to start with your modeling exercise. All right, or the project work. All right. I'm going to stop the recording now. We'll have a little bit of a